Section 6.6, another full testing example, testing with files. In most cases, you'll be able to test your code by adding examples to the docstring like we did in the previous example. However, there are times when testing can be a bit more challenging. This is true when you need to test your code against some kind of external input. An example is when we need to test code that interacts with external websites, but this is more common in advanced code than the kind of code you'll be creating within the scope of this book. An example that is within the scope of this book is working with files. How do you write test cases when your input is a file? Python does support doing this in a way internal to the docstring here, but for continuity with what we've already done, we're not going to do it that way. Instead, we'll use external files to test our code. Let's see how to do that by revising our NFL quarterback, QB, example from Chapter 2. We could walk through an example with the entire file, but because our queries about quarterbacks were only for the first 9 columns of the file, we're going to strip off the remaining columns of the file to make things more readable. After stripping off the remaining columns, Table 6.2 shows the first 4 rows of the file.
Table 6.2, the first 4 lines of an abridged version of the NFL dataset.
We'll assume that each row in the dataset has just these 9 columns for the remainder of the example, but we hope it's not a big stretch to imagine how to do this for the full dataset. You just need to add all the additional columns in each case. Suppose we want to make a function that takes in the file name of the dataset and the name of a player as input and then outputs the total number of passing yards that player achieved in the dataset. We'll assume that the user will be providing the data as formatted in the NFL offensive stats file in Chapter 2 and in Table 6.2. Before we write the prompt or function, how should we test this? Well, we have some options. Find tests in the larger dataset. A solution is to give the full dataset to the function and multiple player names as inputs. The challenge is figuring out whether we're correct or not. We could open the file in software such as Google Sheets or Microsoft Excel and use spreadsheet features to figure out the answer for each player. For example, we could open the file as a sheet in Excel, sort by player, find a player, and use the sum function in Excel to add up all the passing yards for that player. This isn't a bad solution at all, but it's also a fair bit of work, and if you put enough time into finding the answer for testing, you might have already fulfilled your needs and no longer require the Python code. In other words, figuring out the answer for the test cases might just give you the answer you wanted in the first place, making the code less valuable. Another problem is in finding all the edge cases you might want to test. Will your dataset have all the edge cases you'd want to test to write a program that will work on other datasets later? Yet another drawback of this approach is determining what you do when the function is doing something considerably more complicated than just summing a value in a bunch of rows. There, figuring out the answers for some real test values might be a great deal of work. Create artificial dataset or datasets for testing. Another solution is to create artificial datasets where you know the answer to a number of possible queries. Because the dataset is artificial, you can add edge cases to see how the code performs in those cases without having to find such rare examples in the real dataset. Sometimes the real dataset won't include those edge cases, but you still want to test them so the code behaves properly if you get an updated or new dataset. Given the advantages to creating test cases in an artificial dataset, we're going to proceed with that approach here. Section 6.6.1. What tests should we run? Let's think through the common cases and edge cases that we would want to test. For common cases, we'd want to have a few tests. A player appears multiple times in different rows of the dataset, non-consecutively, including the last row. This test makes sure the code iterates over all the players before returning a result. That is, doesn't make the false assumption that the data is sorted by player name. A player appears in consecutive rows of the dataset. This test makes sure there isn't some kind of error where consecutive values are somehow skipped. A player appears just once in the dataset. This test makes sure that the sum behaves properly even when it's just summing one value. A non-quarterback could appear in the dataset. For this, we ensure the code is including all players, not just quarterbacks. A player has 0 total passing yards in a game. This checks to make sure that the code behaves properly when players don't have any passing yards. This is a common case to test because players can get hurt and miss a game due to the injury. For edge cases, we'd want to test a couple more things. The player isn't in the dataset. This is actually pretty interesting. What do we want the code to do in this case? A reasonable answer is to return that they passed for 0 yards. If we ask the dataset how many yards LeBron James, a basketball player, not a football player, passed for in the NFL from 2019 to 2022, 0 is the right answer. However, this may not be the most elegant solution for production code. For example, if we ask for the passing yards for Aaron Rodgers, misspelling Aaron Rodgers, we'd rather have the code tell us he's not in the dataset than that he passed for 0 yards, which could really confuse us when he won the league MVP twice during this time frame. To signal that the name was missing, we might return a large negative value, for example, -9,999. Or we might use something called exceptions, but they are beyond the scope of this book. A player has a negative total number of yards across all games, or a player has a single game with negative yards to ensure the code is properly handling negative values. If you don't follow American football, this can happen if a player catches a ball and is tackled behind the starting point, line of scrimmage. It's unlikely a quarterback would have negative passing yards for an entire game, but it could happen if they throw one pass for a loss, negative yards, and get hurt at the same time, causing them to not play for the rest of the game. Now that we have an idea of what we want to test, let's build an artificial file that captures these test cases. We could have split these tests across multiple files, which would be a reasonable choice to make as well. But an advantage of putting them all in one file is that we can keep all of our test cases together. Table 6.3 is what we built and saved as test_file.csv.
Table 6.3. Our file to test the NFL passing yards function.
Notice that the data here is entirely artificial. These aren't the real statistics for any player, as you can tell by the fact that Dan and Leo are now magically NFL quarterbacks. We did keep the names of some real players, as well as real game IDs and player IDs from the original dataset. It's generally a good idea to make your artificial data be as close to real data as possible, so that the tests are genuine and more apt to be representative of what will happen with real data. Let's look at how we incorporated all the test cases in this test file. Table 6.3. Aaron Rodgers occurs multiple times in the file, both consecutively and non-consecutively, and as the last entry. Jared Goff appears multiple times, and we gave him an artificial -10 yards in a game. As an elite NFL QB, I hope he's okay with us giving him an artificially bad single game. We kept Kerryon Johnson as a running back, RB, from the real dataset, and gave him 5 passing yards to make sure the solution doesn't filter for only QBs. Kerryon Johnson also only has 1 entry in the data. We added Leo Porter to the dataset and gave him 0 passing yards. He's pretty sure he'd do anything to not get tackled by an NFL player. We also added Dan Zingaro and gave him a completed pass, but for -10 yards, covering the case that a single player's total is negative. Table 6.4 shows what it should return per player when we run the query for each player.
Table 6.4. Passing yards per player in the test case.
Section 6.6.2, creating the function. Let's start with the function name and describe the problem in the docstring. This problem may be complicated enough that we'll need to offer prompts within the function to help it know to open the file, process the data, and close the file. But let's try to just describe the function first and see how Copilot does.
Listing 6.9. Function to find total passing yards per player.
Before looking at the code produced, we want to point out that we didn't include the test cases for this example because they likely wouldn't help Copilot. We recommend having Copilot generate code prior to you adding test cases if your test cases will simply open and use artificial files. Each test case will just be a file name, a player, and the expected output. Copilot likely can't read the file that corresponds to that file name and figure out that we're summing the 8th column to get the desired result. This means that giving Copilot the test cases isn't going to add to the quality of the prompt. In fact, the artificial nature of our data might even confuse it. For example, in what scenario does a real NFL player have a negative total for passing yards? Now, looking at the code that Copilot gave us, we can see that it's quite reasonable and almost identical to the code we saw in Chapter 2. Given that it seems reasonable when we read it, let's see how to test it. Section 6.6.3. Testing the function. To test the function, we'll augment the docstring to include our test cases for the full piece of code, as shown in the following listing.
Listing 6.10. Testing the function to find player passing yards.
We ran this code, and all the test cases passed. We know that all test cases passed because there was no output from doctest. we now have additional evidence that the code is functioning properly. Section 6.6.4, Common Challenges with DocTest. Let's rewrite the previous prompt and add a really subtle error to the first test, as shown in the following listing.
Listing 6.11, Mistaken DocTest.
When we ran this code, we received this error.
See this code?
On first glance, this seems really odd. The test case expects 800 and it got 800, but it's telling us it failed. Well, it turns out that we made a mistake in writing the test case and wrote 800, with a space at the end, rather than 800. This mistake causes Python to think the space is important and causes the test to fail. The bad news is that this is a really common problem working with DocTest. We've made this mistake more often than we'd like to admit. The good news is it's really easy to fix by just finding and deleting the space. If a test is failing but the output from DocTest suggests that it should be passing, always check ends of lines for spaces or extra or missing spaces anywhere in your output compared to exactly what DocTest is expecting. Given that all our test cases passed, we can feel confident returning to the larger dataset and using the function we just created. The key thing from this example is that we can and should create artificial files to test functions that work with files. Again, testing is all about gaining confidence that the code is working properly, and you want to be sure you test any code you write or given to you by Copilot. In this chapter as a whole, we learned about the importance of testing code, how to test code, and how to do it in 2 detailed examples. In our examples, we wrote and tested functions. But how do we decide which functions should be written to solve even larger problems? Well, we figure that out through a process known as problem decomposition that we'll cover in detail in our next chapter.